So how did a Scottish engineer change naval warfare forever? Somewhere near the English Channel in the autumn of 1944, a Royal Navy officer is standing in a muddy field in northern France. He's staring at a piece of German engineering that has absolutely no business working as well as it does. The field belongs to a V1 launch site. It's the kind of place that until recently had been throwing flying bombs at London at a rate of several hundred per day. The Germans had abandoned it in a hurry. The Allied advance had pushed them back faster than anticipated, so the launch ramp, the chemical storage bunkers, and the machinery that made the whole thing work were still largely intact. The officer's name is Commander Colin Campbell Mitchell, and he's not here to blow it up. He's actually here to learn from it. Welcome back to the Jackson Talks channel. So this is part 2 of our series on the development of aircraft catapult systems. If you haven't watched part 1, press pause and go and watch that video. The short version is that from 1903 onwards, Navy spent the best part of 40 years invented more creative ways to throw aircraft off ships. They'd used compressed air, gunpowder charges, and even hydraulic pistons with elaborate wire and pulley systems. By the end of the Second World War, they had the technology more or less figured out. Well, they did for propeller aircraft anyway. Then, the jet engine turned up, and that broke everything. So today we're covering what happened next. How a Scottish marine engineer standing in a captured V1 launch site in 1944 saw a solution to a problem that would not fully crystallise for another 5 years. It's how he built a prototype at Edinburgh that the United States Navy initially refused to look at, but then had to come crawling back on its hands and knees to adopt. How that prototype became the technology that made nuclear deterrence viable at sea. This is the story of the steam catapult. It starts with a doodlebug, Commander C.C. Mitchell, and an idea that just wouldn't die. Colin Campbell Mitchell was born in Edinburgh in 1904. He studied engineering in the University of Edinburgh and graduated with a Bachelor of Science in 1925. He spent the interwar years working at a Scottish marine engineering firm, McTaggart, Scott and Company. It was the kind of job that made unglamorous but essential machinery that kept ships working. By the 1930s, Mitchell had become fascinated by the engineering problem of aircraft launch systems. Specifically, he thought that the hydraulic catapults that had become standard on Royal Navy carriers were fundamentally limited. Not bad exactly, not even wrong, just limited in application. The problem as Mitchell saw it was architectural. A hydraulic catapult works like this. A hydraulic ram in the form of a piston inside a cylinder is driven by high pressure fluid. This piston moves perhaps 3 or 4 feet. This motion is then multiplied through an elaborate system of wire ropes threaded through multiple sets of pulleys. In the same way that a block and tackle arrangement lets you lift a heavy object with less force, except in reverse, converting a short, powerful stroke into a longer, faster one. It meant that you could haul the launch carriage and the aircraft attached to it down the full length of the catapult track. The wire and pulley system was, in Mitchell's view, the Achilles heel of the whole arrangement. Those wires were under enormous tension. They stretched and fatigued. They were a constant source of breakdowns and maintenance headaches. They also imposed a hard ceiling on how much energy you could actually deliver to the aircraft, because at some point the tensile strength of the wire itself became the limiting factor. You could only make the wire so thick. In fundamental engineering terms, you were running into a wall. Mitchell's solution, which he patented in 1936, was elegant in simplicity. Remove the troublesome pulleys and wires. Instead, run a slotted cylinder, essentially a very long tube with a groove cut along its top, down the full length of the catapult track. Inside the cylinder, place a piston, and then attach the launch shuttle directly to the top of the piston through the slot. Instead, he ran a slotted cylinder, essentially a very long tube with a groove cut along its top, down the full length of the catapult track. Inside the cylinder, he placed a piston, and then attached the launch shuttle directly to the top of the piston through the slot. He could then drive the piston directly with a single continuous stroke along the length of the cylinder. No wires, no pulleys, just a piston in a slot and a shuttle. The Admiralty looked at it and agreed it was a sound principle, but they filed it away in a maybe but not yet draw. There wasn't an urgency to change at this point. Naval aircraft of the day were still relatively light biplanes. The existing hydraulic catapults worked well enough. Then the war came, and Mitchell joined the Royal Navy Volunteer Reserve, eventually rising to Commander of the Staff of the Admiralty Engineer-in-Chief. His job was flight deck machinery, arresting gear and catapult systems. He spent the war refining and maintaining the equipment that was already in service, even as he kept turning over in his mind the question of what came next. This eventually led him to that field in France in the autumn of 1944. The German V-1 flying bomb, the vengeance weapon, the doodlebug, the buzz bomb, the thing that had been making Londoners' lives misery since June of 1944, was basically launched from a ramp. Specifically, it was launched from a 50-metre inclined ramp using a steam-powered catapult. The mechanism was ingenious. The steam was not generated from a boiler in the conventional sense. Instead, a chemical reaction between two stored compounds, hydrogen peroxide and potassium permanganate, was used to generate large quantities of steam almost instantaneously. This steam was fed into the base of the tube running the full length of the ramp. Inside the tube was a piston, connected to the V1 via a hook that protruded through a slot in the top of the tube. When the steam pressure built sufficiently, it broke the retaining pin, the piston accelerated the length of the ramp, and the V1 was flung off the end at roughly 250 km per hour. This was fast enough for the pulse jet engine to take over and sustain flight. Mitchell looked at the mechanism and saw his own 1936 pattern staring back at him, implemented at full scale and working perfectly. The Germans had independently and for entirely different purposes proved his concept. The slotted cylinder worked. The direct acting piston worked. All that was needed was a better power source than the unstable chemicals stored in the bunkers. Mitchell gathered components from the captured site through the British Intelligence Operations Survey Team. He then took them back to Edinburgh and then went to work. When Mitchell was demobilised from the Royal Navy Volunteer Reserves in 1946, he joined Brown Brothers and Company Limited. They were a marine engine firm based in the Broughton Road in Edinburgh. This was exactly the kind of place where a man of Mitchell's ideas and skills could develop something serious. Under a government contract, Mitchell resumed development of his catapult concept. The key innovation over the V1 launcher was through the selection of a power source. Instead of the volatile chemicals generating instantaneous steam, Mitchell's design would use the ship's own boilers. The same boilers that drove turbines, heated the ship, and powered the ancillary systems. The steam was already there. It was already being generated. You just needed to pipe it to the catapult, store it in an accumulator, and then release it in a controlled burst. This sounds simple, right? However, in practice it required an enormous amount of careful engineering. The initial design used what Mitchell called low-pressure steam at approximately 600 pounds per square inch. This is considerably lower than you might use to launch a 20-ton aircraft. The trick was the accumulator, a large reservoir of steam held at the right pressure, released through a valve at precisely the right moment. This would then drive the piston from a standing start to full velocity over the entire length of the cylinder in a smooth, controlled, accelerated profile. The smooth acceleration was, as it turned out, one of the system's greatest advantages. A hydraulic catapult, with its wire and pulley arrangement, had the characteristic acceleration curve that was anything but smooth, because the pulley geometry meant the force multiplier changed as the system moved. The aircraft experienced a sharp kick, but reached maximum acceleration very early in the stroke. But then it fell off. Pilots described it as a punch in the back followed by nothing. Not dangerous at the weights they were dealing with, but definitely not ideal. Mitchell's steam catapult, driving a piston directly down a cylinder, could be engineered to build its force progressively, accelerating the aircraft smoothly and reaching peak force about 2/3 of the way down the stroke, then easing off as the aircraft left the deck. For a fighter pilot doing 150 miles an hour on the stroke, the difference was significant. For a heavier nuclear bomber, it would be the difference between a viable launch system and one that shook the airframe apart. The prototype, designated BX-S1, was built and tested on shore first, a standard practice, since you didn't want your first launch attempt to be at sea. The land test was a success. The Admiralty really liked what they saw and were convinced. The next step was fitting the thing onto a ship. HMS Perseus had not had a particularly glamorous war. Laid down as a Colossus-class light fleet carrier in 1942 and launched in 1944, she had been redesignated as an aircraft maintenance carrier while still under construction. That meant her aft flight deck was obstructed by maintenance equipment, and she never actually had been fitted with the catapults. She had spent her wartime service carrying spare aircraft to the British fleet in the Pacific, spending more time as a floating parts depot than a fighting ship. After the war, Perseus sat in reserve until 1949, when she was selected as the first test platform for Mitchell's steam catapult. There was no full fleet carriers available for the purpose. The Royal Navy's operational carriers were too valuable to tie up in extended trials. Perseus's unmodified forward deck area provided exactly the clear space needed. Between 1949 and 1951, the prototype BX-S1 steam catapult was built into the new structure of the forward flying deck. The installation required a full refit, with steam piping routed from the ship's boilers to the new accumulator system. The slotted cylinder mechanism was embedded in the deck and all the associated controls and safety equipment put in place. The catapult was at this stage a bit slow to operate, as there was an interval of roughly 20 minutes between launches while the accumulator recharged from the boilers. But for trial purposes, this was entirely acceptable. In the spring of 1951, trials began properly. The methodology was, in true Royal Navy tradition, conservative and sensible. They started launching dead loads, a wheeled metal weight of gradually increasing mass to calibrate the system and verify it was delivering the expected forces. Then came surplus aircraft with their engines removed and their wings folded to test mechanical interference. Then powered aircraft with pilots. Among the test pilots who flew those early launches was Captain Eric Brown. Eric Winkle Brown was the Royal Navy's most experienced test pilot, a man who would eventually accumulate more carrier landings and more aircraft types flown than any pilot in history. Brown's assessment of the steel catapult launch experience was characteristically measured and precise. The acceleration was smooth, the handoff to free flight was clean, and the system clearly had the headroom to handle much heavier aircraft. Over the course of the trials on HMS Perseus, more than 1,500 launches were completed. The BX-S1 proved reliable. It proved consistent. It proved that Mitchell's concept was not just theoretical sound, but practically viable at the scale needed for a real aircraft carrier's operations. The Admiralty was delighted, but there was another audience that needed convincing, and they were going to take a little more work. While Mitchell was perfecting the steam catapult at Brown Brothers in Edinburgh, the United States Navy's Bureau of Aeronautics was working on the same problem, but from a completely different direction. At first, they were not interested in Mitchell's solution. The American problem was specific and urgent. The Douglas A-3D Sky Warrior. This was the aircraft the United States Navy wanted to operate off its carriers. It was a twin-jet nuclear bomber with a range better than 1,000 miles, capable of delivering hydrogen bombs to targets deep in the Soviet Union. It was, by any measure, a serious aeroplane. Fully loaded, it weighed in the region of 78,000 pounds. That's approximately 35 tons. Roughly 3 times the weight of contemporary jet fighters. The hydraulic catapults in service on the American carriers, the most powerful of which was the H-8, could barely manage the A.J. Savage, a relatively modest, short-range nuclear bomber. The Sky Warrior needed something entirely different. The H-8's wire and pulley arrangement simply did not have the energy capacity to launch 35 tons to flying speed in just 300 feet. The Bureau of Aeronautics proposed a solution that they called the gun catapult. In concept, this was essentially exactly what it sounds like, a very large gun. This was built into the carrier's flight deck and fired propellant charge to drive a piston, the launch shuttle, and the aircraft attached the length of the catapult track. No pulleys and no wires, just direct force acting like Mitchell's design. Just powered by a controlled explosion rather than steam. The Bureau had considered steam and rejected it. Their reasoning, documented at the time, was that steam pressure from ship boilers varied too much with the ship's operational state. If you were running hard on the engines, demanding full power for the propulsion system, there might not be surplus steam available for the catapult. An explosive charge, by contrast, was self-contained, consistent and predictable. What the Bureau perhaps didn't think about was the other side of the ledger. An explosive catapult required a very large supply of propellant charges to be stored on the carrier. A carrier intended to fly multiple sorties per day would need to carry thousands of these charges in its magazine. The logistics were formidable, and the fire risk not trivial. But then, there was the elephant in the room. The gun catapult didn't actually work. Through the late 40s and into the early 1950s, the American explosive catapult program struggled. The engineering challenges of building something that was essentially a low-velocity artillery piece into a carrier flight deck, all the while maintaining the reliability and safety standards required for routine aviation operations, proved considerably more difficult in practice than on a drawing board. The program fell behind schedule. Meanwhile, the A3D was reaching its prototype stage on time. The aircraft existed, but the catapult to launch it did not. The British had been sharing information about steam catapult development through this period, as the two navies had a long-standing practice of technical information exchange. But the Americans weren't interested. They had considered steam and had rejected it. They were not going to reconsider simply because the British thought their version would work. This was the situation until late 1951. The gun catapult program was years behind schedule, possibly terminal. The Sky Warrior was coming, and if something didn't change very quickly, the United States Navy was going to find itself unable to fulfill its nuclear mission. The man who saved the United States Navy's nuclear aviation program was Rear Admiral Apollo Souchek. He was the US Naval Attaché in London, and he was an aviator who understood carrier operations from the inside. He'd been following the development of the British steam catapult closely, and unlike his colleagues in America, he understood exactly what was at stake. So Souchek went over their heads. He went to the office of the Chief of Naval Operations and made the case with considerable force. The explosives catapult was not going to be ready, and the A3D was. The British, they had a working steam catapult aboard a ship at this moment, and that ship, HMS Perseus, needed to come to the United States for demonstration trials immediately. The Chief of Naval Operations agreed, and on December 1951, HMS Perseus crossed the Atlantic and arrived in American waters. Tests were conducted between December of 1951 and February of 1952. The US Navy supplied dead loads and operational aircraft for the trials. A destroyer, USS Green, provided additional steam pressure higher than the British naval practice to test whether the catapult could handle American boiler outputs. 140 launches were conducted. The data was compared to the Royal Navy's own trial reports. It correlated well. The system was adaptable to American ships. Critically, and this is the detail that tends to get lost on the broader story, the Americans found that the steam catapult at higher pressure could deliver considerably more energy than the British were using. The BXS-1 prototype on the Perseus was already capable of handling aircraft heavier than anything the Royal Navy expected to operate in the foreseeable future. Pushed to American boiler pressures, it could handle the Sky Warrior. The United States Navy adopted the steam catapult. They acquired the manufacturing rights from Brown Brothers and Company under a Mutual Defense Assistance Plan, and work began in the United States in April of 1952. The American version of the system was designated C-11, and on the 17th of June 1954, USS Hancock, which had spent 3 years in refit, made the first steam catapult launch from an American aircraft carrier. The aircraft was a Grumman S-2F1 tracker anti-submarine aircraft. The pilot, according to contemporary records, found the launch unremarkable in the best possible way. It had worked exactly as advertised. HMS Ark Royal, the Royal Navy's new fleet carrier, received their own steam catapults in February of 1955. So the British, who invented the damn thing, got the first operational steam catapult installation several months after the Americans, who had initially refused to look at it. This is a pattern that repeats itself in some regularity in the history of British military technology, particularly after World War II. Invent something, share it with the Allies, watch the Allies implement it faster, and then repeat. To understand why the steam catapult mattered so much in strategic terms, you need to understand nuclear calculus in the early 1950s. The United States had nuclear weapons. The Soviet Union, from 1949, also had nuclear weapons. The Cold War was not as yet mutually assured destruction standoff of the 1960s, because neither side had developed intercontinental ballistic missiles in operational numbers. Nuclear delivery in 1952 still needed aircraft. Heavy bombers, specifically it meant B-36 Peacemakers and B-47 Stratojets, operating from fixed land bases. Bases whose locations were well known to Soviet intelligence, and therefore, in the event of war, among the first targets that would be struck. The carrier offered something that land-based bomber could not: mobility. A carrier operating in the Norwegian Sea, the Mediterranean, or the Western Pacific could launch nuclear strikes against targets that land-based aircraft could not. All this from a platform that was moving and therefore considerably harder to destroy and target. The carrier, with the right aircraft, was a roaming nuclear threat that no fixed defensive system could reliably neutralize. The Douglas A3D Sky Warrior, which entered service in 1956, redesignated the A3, was the aircraft that made this concept real. At £78,000 fully loaded, with a combat radius of over 1,000 miles, they had the ability to carry a nuclear weapon in its internal bomb bay. The Whale, as its crews inadvertently nicknamed it for reasons of aerodynamic equivalence, was exactly what the carrier's nuclear mission required. Without the steam catapult, the Whale could not have operated from a carrier at all. The hydraulic systems of the early 1950s simply couldn't generate enough energy. The steam catapult in the form of the C-11 and its successors was not just a useful improvement, it was an enabling technology that made sea-based nuclear deterrence viable. It changed the strategic balance of the Cold War. That is not a small thing to attribute to a Scottish engineer with a 1936 patent and a revelation in a muddy field in France. That said, the steam catapult did not arrive in isolation. It was part of a broader revolution in carrier design that took place in the early 1950s, a revolution that, with some British irony, was driven almost entirely by British innovations. The angled flight deck, for example. That arrangement, where the landing area is angled roughly 9 degrees away from the ship's centerline. This allowed an aircraft that misses the arresting wires to go full power and fly off the angled deck without hitting aircraft parked forward. This was invented by a Royal Navy officer named Captain D.F. Campbell in 1951. It was tested on HMS Triumph and USS Hancock before becoming standard on every carrier built thereafter. The mirror landing aid, which was basically a gyroscopically stabilized, illuminated mirror that replaced the deck landing control officer's bats, giving pilots a continuous indication of the glide path. This was invented by a Royal Navy Lieutenant Commander Goodhart in the early 1950s. It was adopted by both navies and is the ancestor of the lens optical landing system still in use today. Then there is Mitchell's steam catapult. That was the third element of the Trinity. Together, these three innovations transformed carrier aviation from its Second World War form into something recognizable and modern. The angled deck made simultaneous launch and recovery operations safe. The mirror landing aid reduced landing accident rate dramatically, and the steam catapult provided the energy to launch aircraft that the hydraulic system could not. The USS Forrestal, commissioned in 1955, was the first carrier designed from the keel up to incorporate all three of these systems. She was also the first American carrier specifically designed to operate the Sky Warrior. It's why she was built in the dimensions she was, with a 1,063-foot flight deck, 4 steam catapults, 2 on the angled deck and 2 on the bow, maximum flexibility, maximum launch rate. Forrestal was followed by Saratoga, Ranger and Independence, which completed the Forrestal class. The next big leap was the USS Enterprise, the world's first nuclear-powered carrier, commissioned in 1961, with 8 reactors, 4 catapults, and a theoretical aircraft operating capability that no propulsion-limited ship could match. The nuclear carrier could steam indefinitely at full speed, maintaining a 30+ knot headwind over the deck that made catapult operations most efficient, without ever running short of fuel. Her reactors also powered the steam that fed her catapults. Nuclear power and steam catapults were, as it turned out, an exceptionally elegant pairing. The reactor powered heat, that heat produced steam, which in turn drove the turbines and powered the ship, and that same steam, drawn off before the turbines, loaded the catapult accumulators ready for the next launch. At this point, it's worth taking a moment to actually explain what happens during a steam catapult launch, because the physics is genuinely interesting, and because if you never stood on a carrier flight deck and watched what happened up close, the scale of what's occurring is easy to underestimate. As said before, the catapult track runs below the surface of the flight deck. What you see from above is the slot, roughly 2 inches wide, running the full length of the catapult. Through this slot protrudes the launch shuttle, a piece of hardened steel that rides on top of the piston inside the cylinder below. The aircraft is attached to the shuttle by a launch bar, a hook built into the aircraft's nose wheel that engages the shuttle. A holdback bar at the rear of the aircraft connects to a fixed point on the deck, keeping the aircraft stationary while the catapult pressurizes. At this point, the pilot runs the engine up to full middle power, or on aircraft where it's appropriate, afterburner, and holds it there. The catapult crew verify that everything is connected, that the weight setting is correct for the aircraft's launch weight, and the steam pressure in the accumulator is appropriate. The catapult officer gives a signal. The valve opens, steam flows from the accumulator into the cylinder. The pressure behind the piston rises in a controlled surge. The holdback bar reaches its designated braking load. It's engineered to shear at a specific force and snaps. In approximately 2 seconds, on a 300-foot stroke, the aircraft goes from 0 to roughly 150 miles an hour. For anyone on board, this means experience a sustained force of approximately 3 Gs. For a person, say weighing 180 pounds, They effectively weigh up to about 540 pounds for those 2 seconds. If they're wearing a flight suit, helmet, oxygen mask, G-suit, survival vest, and all the ancillary equipment of a naval aviator, the total is considerably higher. At the end of the stroke, the shuttle hits a water break, a hydraulic buffer that stops the piston dead, preventing it from flying off the bow of the ship. The aircraft, now at flying speed, continues forward off the deck. The shuttle is then retracted, the holdback is replaced, the accumulator recharges from the boilers, and the next aircraft is moved into position. On a modern Nimitz-class carrier, with all 4 catapults operating simultaneously, the ship can theoretically sustain a launch rate of 1 aircraft every 30 seconds at peak effort. From Mitchell's 1936 pattern to this sortie rate took about 20 years, and it has remained essentially the same system for another 70. The steam catapult's operational career spans virtually every American military engagement from the late 1950s to the present day. Vietnam, the Gulf War, Libya, and dozens of smaller, less publicised operations that never made it into the evening news, but required an American carrier aviation to be present and functional. The Nimitz-class nuclear power supercarriers that became the backbone of the US Navy's carrier force from the 1970s onwards were built around the C-13 and C-13-1 steam catapult, the evolutionary descendants of Mitchell's original design. The C-13 was longer than the C-11 fitted to the Hancock and the Forrestal class, generating more energy, with enough to handle aircraft considerably heavier than the original design requirement. As aircraft grew heavier and faster through the Cold War decades, the catapult grew with them. The same fundamental principle, just bigger numbers. During the Vietnam War, USS Constellation, USS Coral Sea and USS Kitty Hawk and their sisters operated almost continuously in the Gulf of Tonkin. Their catapults launching hundreds of sorties per day during peak operations. At the height of Rolling Thunder and Linebacker, an American carrier on a Yankee station might launch and recover 200 aircraft in a single day. 4 catapults working in rotation, each cycle taking a minute or 2 to reset. The numbers are staggering in retrospect. The catapult crews, or the shooters in the carrier parlance, became some of the most highly trained technicians in the Navy. A catapult officer responsible for setting the steam pressure correctly for the launch was, in quite literal terms, holding a pilot's life in his hands. Too little pressure, and the aircraft would not reach flying speed at the end of the stroke, resulting in a cold cat shot. Too much pressure, and the launch engine could damage the aircraft's structure. The weightboard, the card listing each aircraft's exact launch weight, was as sacred a document on a carrier flight deck as the flying schedule. Cold cat shots did happen. They were rare, but they happened. There are famous photographs of aircraft at the moment of departure from the end of a carrier's bow, clearly already too slow, the nose beginning to droop. Some of these pilots survived. Sadly, some did not. The steam catapult, for its engineering elegance, was not a forgiving system when something went wrong. The Royal Navy, meanwhile, had made a different calculation. Facing defence budget cuts through the 1960s, the decision was taken to retire the conventional carrier force, with the last British fleet carrier, HMS Perseus, paid off in 1979. British carrier aviation spent the 80s and early 90s operating from smaller 3-deck cruisers, the Invincible class, using ski jump ramps and the short takeoff and vertical landing capabilities of the Harrier jump jet. No catapults required, a significant capability reduction, but one the defence budget of the era dictated. British carrier aviation only returned to the catapult question with the design of the Queen Elizabeth class, the current generation of British carriers. But even then, after considerable debate, the decision was made to go with the ski jump again, this time though with the F-35Bs, rather than incur the additional cost and complexities of fitting catapults. The Queen Elizabeth and the Prince of Wales, although magnificent ships, cannot at present operate conventional carrier aircraft. That said, the steam catapult's adoption was not limited just to the United States. The fundamental logic of the system was compelling enough that any navy with the aspiration and the budget to operate a full conventional carrier eventually came to the same conclusion. France, which has maintained an independent carrier strike capability since the 1960s, built its first purpose-designed nuclear-powered carrier, the Charles de Gaulle, around the steam catapult system, commissioning her in 2001. The Charles de Gaulle uses a shortened version of the American C-13 catapult, adapted for her deck dimensions. She operates Rafale Marine fighters and the E-2 Hawkeye airborne early warning aircraft. She remains the only non-American nuclear-powered carrier in service. China has been the most recent arrival on the catapult conversation. The Fuyan, China's third carrier, is the first designed entirely domestically and commissioned in 2024. equipped not with steam catapults, but the next generation of technology, which brings us to the ending of the steam catapult story. The steam catapult is not in the end a perfect technology. It is a remarkable one, it's a proven one, and it has launched millions of sorties in 70 years of service, and it continues to perform with great reliability on the 10 Nimitz class carriers in active service. But it has limitations that have become increasingly apparent as carrier aviation has evolved. The first limitation is energy control. A steam catapult delivers energy in a profile that's difficult to fine-tune for different aircraft weights. The system is calibrated for a given weight range, and the margin of error is not generous. In the Second World War era, this was less of a problem, because aircraft weights were relatively consistent. Modern carrier wings, by contrast, might include everything from 60,000-pound E-2D Hawkeyes to the relatively light unmanned aerial vehicle. A steam catapult that's tuned for an F-18 Super Hornet is not an ideal for a lightweight drone, for example. Now, you can work around it, but you cannot tune it precisely. The second limitation is maintenance. A steam catapult is an extremely complex piece of machinery. The cylinder, the piston, the valves, the accumulators, the water brakes, the steam piping, all of it requires constant and meticulous maintenance by highly trained specialists. A Nimitz-class carrier, for example, devotes a significant portion of its engineering manpower to catapult maintenance. The system requires fresh water for water brakes. This means a constant demand on the ship's desalination capacity. Steel piping at high pressure in a seawater environment is not a low-maintenance proposition. The third limitation, and less talked about, but increasingly significant, is the physical violence of the launch itself. A steam catapult launch and its characteristic force profile imposes loads that don't usually appear in most aircraft's flight envelope. When you take this over hundreds of thousands of launch cycles, this contributes to airframe fatigue and the potential early retirement of an aircraft. Heavier maintenance cycles, higher whole life costs, these are problems that the Electromagnetic Aircraft Launch System, or EMALS, is designed to solve. EMALS was developed by General Atomic for the United States Navy. It uses a linear induction motor, the same electromagnetic principle that's used on maglev trains, to accelerate the launch shuttle. Instead of steam expanding behind a piston, an electromagnetic field travels down the catapult track, dragging the conductive shuttle along with it. The force applied to the shuttle, and therefore to the aircraft, can be precisely controlled throughout the stroke. The advantages over steam on paper are compelling. Smoother acceleration, precise energy control for any aircraft, any weight, whether it be a light drone or a heavily loaded strike aircraft. No high pressure systems, no water brakes, no fresh water demand, and fewer moving parts. On a nuclear carrier, the electricity it runs on comes from the reactors, with no fuel costs beyond the reactor's existing output. The USS Gerald R. Ford, the lead ship of the new Ford class, commissioned in 2017, was built around an EMALS, and its companion system, the Advanced Arrestor Gear. The Navy projected considerable improvements in sortie generation rates and dramatically reduced maintenance requirements compared to the Nimitz class. What actually happened was a considerably rockier process. In testing through 2019 to 2020, the EMALS system upon the Ford achieved a reliable figure of about 181 mean cycles between operational mission failure, against a design target of over 4,000, which is to say it was breaking down roughly 20 times more frequently than designed. The Advanced Arrestor Gear had similar struggles. Now, the systems were complex. The integration into the ship's electrical plant were difficult under operational conditions. This led to the Ford spending considerably more time in post-delivery testing and trials than they actually planned. That said, the Navy maintained that working the problems out during this test phase was exactly what the phase was for, and that the systems were improving continuously as the crew gained experience. By 2022, Ford had accumulated over 8,000 launches and recoveries on EMALS. By a first operational deployment in 2022 in the Mediterranean and then the Eastern Atlantic, the systems were performing well enough for sustained fleet operations. The reliability picture, while still not at the design target, was improving. The second Ford-class carrier, USS John F. Kennedy, is undergoing its own EMALS testing at the time of this video. The Enterprise and Doris Miller, Ford classes 3 and 4, are under construction. The French Navy has also expressed interest in EMALS for the next generation carrier, and China's Fuan has what appears to be a domestic version of the system, though the precise technical details remain classified. The age of the steam catapult is not over yet. 10 Nimitz-class carriers will operate the C-13s for years to come, but its successor is clearly here. So let's take a moment and stand back. We started with a two-part series with Lieutenant Commander Henry Mustins being fired off the deck of USS North Carolina in 1915 on a catapult powered by compressed air. We went through gunpowder charges and hydraulic pistons with wire and pulley systems, and camshafts with their one-way hurricane launchers, and the Kingfishers and Walruses and Ardo of 196s, and the whole extraordinary ecosystem of interwar and wartime catapult aviation. Then we got to the jet age, and we met Colin Campbell Mitchell, a Scottish engineer who had an idea in 1936. He filed it away and spent the war maintaining other people's systems. He was then stood in a muddy field and saw what the Germans had done, which proved his concept. He went back to Edinburgh, built his prototype, put it on HMS Perseus, took it to America and convinced the US Navy to abandon the program as it wasn't working. In doing so, made sea-based nuclear deterrence viable in the Western Alliance. Mitchell received an OBE for his work. He's not especially widely known outside of naval engineering and carrier aviation history circles. It's what history books will call criminal neglect, especially if it was concerned with almost any other inventor of comparable strategic significance. The steam catapult that Mitchell designed launched the aircraft that deterred the Soviet Union throughout the Cold War. It enabled carrier aviation as the dominant form of naval power. Every time you watch footage of an F-18 being flung off a carrier deck in a cloud of steam, that cloud, those 2 seconds of violent acceleration, the aircraft climbing steeply away into the sky, you're watching Mitchell's 1936 idea in its operational form. These days, EMALS is taking over, replacing steam with electromagnets, solving the limitations that steam couldn't escape. The same cycle that produced Mitchell identified the limits of the current technology, find a better principle, prove it, implement it, wait for the next generation to push against it and change the limits again. Carrier aviation is, in that sense, one of the great continuing engineering stories of the 20th and 21st centuries. It's never stopped evolving. It has never settled for good enough. And the catapult, in whatever form, remains at its heart. So that's it, folks. Thanks for tuning in to this episode of Jackson Talks. I hope you've enjoyed it. Apologies for my regular listeners that have been waiting very patiently for this episode to come out. I've had some technical issues and moving house, etc., so life does get in the way every now and then. But thanks for tuning in, and I hope to see you on the next episode.